videos on? Yes. On the test? On the... Okay. So lab test. When I do this, it means shut the hell up. Remember, I learned that from my kindergarten teacher. It works. It actually works. That's great. Yes. Both sons. Yeah, I like one a lot more. That's why I only talk about one. Okay, so lab exam 2. Number 2. Did you guys, well, I think different, I had one like this and one upside down. So I'm going to divide it into these points. So first, where is velocity positive and where is velocity negative? That has, what? Oh, that has to do with the slope of the tangent lines at all these points. From A all the way to C, the tangent lines all have positive slopes. Okay, so from A to B, that's a positive velocity, and from B to C, that's a positive velocity. And then from C to E, all of the tangents have negative slopes. And so this whole way, the velocity is negative. Then to figure out whether you have positive or negative acceleration, that has to do with whether it's concave up, like a cup, or concave down, like a frown. From A to B, that's concave up. So that's a positive acceleration. From B to C, concave down. So negative. C to D, it's still concave down. And D to E, it's concave up again. And then the last thing you have to do is figure out whether it's speeding up or slowing down. You can do that just based on looking at these two values on each interval. If they have the same sign, it's speeding up. If they have opposite signs, it's slowing down. So from A to B, it's speeding up. From B to C, it's slowing down. From C to D, same sign, so that's speeding up again. And D to E, it's slowing down again. So when you do these, I think by far the easiest way to do it is just figure out the sign of the velocity, figure out the sign of the acceleration, and then use those, compare those to see whether it's speeding up or slowing down. Yep?
And then also for is it moving in a positive or negative direction?
Oh, yeah. So that is another way of asking what's the sign of the velocity. Mm-hmm. So the direction it's moving is the velocity. So from A, all the way from A to C, it's moving in the positive direction. Yeah. All the way from C to E, it's moving in the negative direction. Okay, sure. All right. Any other questions about that one? Any other questions about the lab test?
Could you please do the position versus time graph for 3B and A? And do A.
Just all of number 3?
Correct.
Okay. So the one you did everybody have the one where the ball's launched up and to the right?
Yep.
Or did some people have like straight up or straight down?
Straight down.
Okay. Well, I'll do both of those. So,
yeah, mine was straight down.
Okay. Did anyone have anything different than that, than a ball thrown straight down? To the right. Okay, I'll do both. Okay, so for a ball thrown straight down, what did it say the positive direction was in the 0 position?
It doesn't. Well, part A and part B are sketch a graph of the position, x component versus time, and then sketch a graph of the position's y component versus time.
Doesn't it say something about the origin and the origin's on the ground with the y-axis up?
Yeah, mine says let the origin be above the ground at the original height of the ball.
Above the ground at the original height of the ball. Okay, so there's just a bunch of different versions. Okay, so the origin is here, and does it say the y-axis is up? So there's the coordinate system. And it's being thrown straight down. If it's thrown straight down, the x position never changes. This ball is going to start out at 0y and go down into negative y values, but that it's never going to move horizontally, so the x position is always going to stay the same. So the x position versus time, I'll write it as px versus time, is just a horizontal line. Ah. I used to have this really useful thing that somehow my hand bumped and I don't know how to get it back. Okay, so it's horizontal. I'll leave it at that. And then the y position versus time. Here's what you know. It starts out with a negative slope because it starts out with a negative velocity. It's being thrown towards the ground. And it also has a negative acceleration because in free fall problems with the y-axis up, that's how this always looks. And so you'll get a curved line with a negative acceleration, concave down, that starts out with a slope below 0. Who has any questions about that one? Okay, so let's do some of the alternate ones. So some people also had this 3 where I think it was also thrown down towards the ground, but this time I think there might have been, did anyone have the ball thrown straight down to the ground with the y-axis, with the origin on the ground? No? Okay. So the one where it's thrown to the right. It's following a path like this. The initial velocity vector is up and to the right. If you thought about, if you put the tail of this initial velocity vector at the origin and thought about the quadrant that vector's in, you know that both of those two components are positive. So what that says is the slope at time equals 0 is positive in both of these two cases. So we have something like this for x and something like this for y. What's the x component of the acceleration for something in free fall? It starts with a z. 0, yes. And so if the x component of acceleration is 0, that means that the x component of the velocity never changes. Okay, so the slope of this graph never changes. It's just a line that keeps that same slope the whole time. And so that's what the, so if you're plotting the x position versus time, it looks like this. Yep.
So maybe I'm just confused, but so then why isn't the graph for the y component of the first one where, well, actually the same as the y component?
The slope of this one stays the same, but also the position stays the same. This one, it starts with a positive velocity, so it does have an x component that's positive. That just never changes. And so what you get is over time, the x position is changing, but the velocity stays the same. And then this one, we know the y position versus time has a negative slope. And so it follows a concave down path starting with a positive velocity. Any other questions about that one? And then the rest of 3 and 4 and 5 and 6 are all pretty much the same question. Just thinking about whether it's speeding up or slowing down, whether it's turning, using that to come up with the total acceleration. Any other questions about the test? All right. The next topic we're going into, before I do that, any questions about the homework? Have you had a chance to work on some of those friction problems and stuff like that? Practice problems. Okay. Yes?
I have a question, but it's about the other one problems on the you just started in class with the acceleration factors with the angle. If you could explain a little bit,
Sure.
like with the axis, how we know where to place the angle.
How to know where to put the coordinate system? So, let's do an example, and I'll try to explain it as I go. So, so let's say we have this incline that makes a 40-degree angle with the horizontal. And there's a box with a mass of 10 kilograms. And we want to know what's the acceleration vector of the box and the force vector applied by the incline. If there's no friction. And then second, we're going to calculate those same things. What's the acceleration of the box and the force vector applied by the incline with a coefficient of kinetic friction of 0.1. All right, so in all of these, whether there's friction or not, we choose a coordinate system where the y-axis points directly out of the surface. And then the x-axis is whatever it has to be for that to be an acceptable coordinate system. So remember, all you can do with the coordinate system is start with the usual one and then rotate it. So if we put the x-axis this way, you can rotate from the original one to this. If I had tried to put the x-axis that way, there's nothing you can do to rotate this to make the y-axis point that way and the x point that way without flipping it, so that's not allowed. Okay, so for part A, we're going to start with a free body diagram. There's a weight force of 10 times 9.81. And then there is a pushing contact from the ground. I'll call that N. And if you go around the boundary of the box, there's nowhere else that anything contacts the boundary. So that's all the forces. And Newton's second law now. The normal force always is the same, just 0n. The weight force now we have to think about. So we have a weight force with a magnitude of 98.1. And our coordinate system is like this. There's an angle on here that's equal to 40 degrees. What is it? Yeah, right. Well, the 40 degrees is here. It's from the 270 line to the vector. And so that means that to come up with the angle, the counterclockwise angle from the positive x-axis to the vector, you go 90, 180, 270, plus 40, so 310. Yep. And so this force vector is 98.1 times the cosine of 310 and 98.1 times the sine of 310. Can someone calculate those for me? 7515 and 6306.
So with the 40-degree angle being right there, I guess that was my question for this problem. So looking at the axes, like if you go above, how do you know? Do you just know that from like the geometry of to put it in that spot?
Okay. So practically speaking, if you just wanted the fastest way to always get it right, just think about however far this incline is from horizontal. Okay, that angle is how far the new weight vector is from that negative y-axis. Okay, so if this is all the way at 90 degrees, your weight force is going to be 90 degrees from that negative y-axis. So that's the easiest answer. Making sense out of it in your head is a little trickier than that, but I think, yeah, but if that always works, I think most people don't care about that. But I'd be happy to talk about that if anybody's curious how you would figure that out on a desert island or whatever if you didn't remember the rule. Because, like, you'd definitely be doing physics on a desert island all by yourself.
The Galapagos Island.
Yeah, maybe. Like, oh, I'm so lonely. I'm going to do some physics. You're like, I'm going to do some physics to figure out how to get this giant tortoise off me. So the weight force is 63.06. negative 75.15. And those two forces add up to the mass times the acceleration. So we have two equations. The x equation says 63.06 is equal to 10a. So a is equal to 6.306. I'll just write it as 6.31 meters per second squared. And then in this particular problem, I guess I did ask for that force. So the acceleration vector is this thing. All we have to do is plug in the variable. And so the acceleration vector is 6.310 in meters per second squared. Oh, and in part A, this didn't come up. It's going to come up in part B. We have to know something about the motion. So let's say that at the instant shown, the motion is down the ramp. Okay, that's the direction of the velocity vector. We're going to use that in part B. So here's a question for you to answer, for me. What if I had said the motion was up the ramp? That doesn't look like it makes any sense, really, right? Could I do that?
Yes.
Yes?
Because motion and acceleration doesn't have to.
That's right, exactly. So think of the direction of the motion that I give you as telling you something about what happened up until this instant, like before this instant. It's possible that for the 10 seconds before this snapshot that I have here, there was a big force pushing this up the hill that got it going really fast. Then that force was removed, and then that was when we wanted to analyze that. So that velocity has to do with the stuff that happened before the instant that we're looking at. The acceleration is different. The acceleration is something that's happening exactly at that instant. It doesn't care about the past or the future. The acceleration just has to do with the forces at that instant.
That sounds really deeply philosophical.
Yeah, that did. I like that. Okay, and now we have to figure out the force applied to the box by the incline. The y equation says n minus 75.15 is equal to 0. So n is equal to positive 75.15 newtons. And in order to make that a force vector, we're going to plug that value of n into this force. You know, that's the force that is applied to the box by the ground. And so I'll write it as the force on the box by the incline. Plug 75 into this vector, and you get 0, 75.15. Yes?
So the question is, in the previous examples, you said that n is always positive. So if we get n as a negative, it means that we did something wrong.
That's right.
Okay.
Okay, so what happened here? So this box was moving down the incline. We got an acceleration vector that was, is it up or down the incline? It's in the positive x direction, so it's down the incline. And so is the box speeding up or slowing down? Any other guesses? Speeding up. So because we know that if the velocity and acceleration are in the same direction, this is the velocity, the acceleration's in the same direction. If they're in the same direction, it's speeding up. If they were in the opposite direction, it would be slowing down. So what are the possible things that we could see when we add friction to this problem? So without friction, it's speeding up down the ramp. Is it possible that friction could make it speed up more? No, that's not possible. Really, that's the only thing that's not possible here. So friction is always trying to slow things down. It might not be enough to make it slow down, but it at least will make it so it speeds up less. Okay? It's also possible that friction will be enough to make it slow down. So we're either going to have an acceleration vector that's in this same direction with a smaller value than 6.31, or we're going to have an acceleration value in the opposite direction. Okay? Yes?
So when you did the natural force vector that's underneath it, this is just a technicality, but you said the force on the box by, just go down a little bit, please.
Yeah.
Would you just be able to say the natural force vector equals that, or?
Yeah, that's fine with me. Yep. Yeah, that's fine.
Okay.
Yep. And by the way, what we found is that that is pointing this direction with a magnitude of 75.15 newtons. Okay, so now let's go to part B. And we'll go back to the free body diagram. So what forces are acting this time? There's still a weight force of 98.1. There's still a normal force perpendicular to the surface toward the chosen body. And now there's also going to be a friction force. The motion is down the ramp, so the friction force has to be up the ramp. It has to be opposite that velocity vector. And I said that the coefficient of friction is 0.1, so this is going to be 0.1 n.
I'm sorry, why is it 0.1?
Because that was given. I just said that the coefficient of kinetic friction was 0.1. So you always multiply that coefficient times the normal. And now Newton's second law. We have the normal force. That's 0n. We have the friction force that's in the negative x direction. So that's negative 0.1 n 0. And then we have the weight force that's just like it was in part A. So I'm just going to take these values. So 63.06, negative 75.15. And those forces add up to be equal to 10 times A0. Yes? It is the same, yeah. I think probably the best approach is just to go through the calculation again, but you're right that it is going to come out being the same.
Is it has to do with the Newton third law? Or why is
With
it
what?
the same?
Why is it the same? The reason it's the same is because the friction force is perpendicular to the normal force, and so it doesn't affect it. Remember, those perpendicular directions are always independent of each other.
And is friction always exactly opposite of acceleration?
Of velocity, not acceleration, yeah.
Okay.
And so these problems will always just tell you it's moving up the ramp, down the ramp, or it'll say this is the velocity direction, or it'll say this is the direction of motion. Something to let you know what the velocity direction is, because without that, you wouldn't know what direction the friction is acting.
Okay, but it's always like exactly opposite, not
Yep.
just kind of.
Always, exactly, right. Okay, so the x, well, so the way we want to do these friction problems, we always do them the same. First, use the y equation to solve for n, and then plug that n value into the x equation to find the acceleration. Okay, that's always the order of things. So first, we're going to use the y equation for n, then plug n into the x equation. So the y equation says n minus 75.15 is equal to 0. So n is equal to 75.15. Then plug that into the x equation, and you get negative 0.1 times 75.15 plus 63.06 is equal to 10a. Or negative 7.52, let's call it, plus 63.06 is equal to 10a. Can someone subtract those for me? Okay, 55.55, so a is equal to 5.55. And then to calculate the acceleration vector, plug that into the acceleration vector that we had in Newton's second law. This one. And you get 5.550. Okay, well, that's the acceleration vector. That's in the positive x direction, and x was going down the incline. So is the box speeding up or slowing down in this part? Speeding up. How does the amount it's speeding up, how does that compare to part A? It's not speeding up as much. Friction is keeping it from speeding up as much. At some point, if you kept increasing the coefficient of friction, you'd get to a point where the friction was enough to make it slow down instead of speeding up. Okay, and then the last thing, it asks for the force vector. It asks for the force vector on the block by the incline. Both of these two things together make up the force vector on the block by the incline. Okay, the friction is applied by the incline also. So we have to include both of these to figure out that force. The normal force was 75.15. So the force on the box, by the incline is equal to 0, 75.15 plus negative 0.1 times 75.15, 0, which is negative 7.52, positive 75.15 newtons. Any questions about that? Okay, here's part C. What coefficient of friction would be required so that the box maintains a constant speed? Okay, so in both of part A and part B, we saw that the box was speeding up, right? And I said if you keep increasing the coefficient of friction, at some point it'll switch over to where friction is enough to slow the box down. So we're going to find the exact coefficient of friction that would be required for that crossover, okay? In order to do that, we need a way to specify when this thing gets to a constant speed. So how are we going to specify that in this problem? That's right. Yep. So it's moving in a straight line, which means there's no perpendicular part of the acceleration. The only other way that there can be acceleration is if it's speeding up or slowing down. And so we're going to say, that requires that the acceleration vector is equal to 0, 0. An acceleration vector of 0, 0 is the same thing as saying constant velocity. You can think of those as synonyms. Can you have a two-word synonym? Probably not. But you can think of those as meaning the same thing. If you look up acceleration of 0 in the dictionary, it says constant velocity. There's not really an entry, and it doesn't actually say that, but okay, so we're going to use the same approach. Free body diagram looks like this. There's a weight force of 98.1. There's a normal force, N. And there's a friction force that's in the opposite direction of the velocity, this way. And what is the magnitude of that friction force? What are we going to call it? Well, it's always equal to the coefficient times the normal force. We don't know what that coefficient is, though, this time. We have to solve for that. So I'm just going to write this as mu sub k times the normal force. And now Newton's second law says 0n plus, this force is in the negative x direction, so negative mu sub k times the normal, 0, plus 63.06, negative 75.15. That's the weight force. That's been the same for every one of these parts. Is equal to the mass of the box times the acceleration, which now we're saying has to be equal to 0, 0 to, in order for the speed to stay constant. Any questions yet about this setup? And so the y equation says n minus 75.15 is equal to 0. So n is equal to 75.15. Plug that into the x equation, and you get negative mu sub k, we don't know what that is yet, times 75.15 plus 63.06 is equal to 0. I'll add mu sub k times 75.15 to both sides. So we get 63.06 is equal to mu sub k times 75.15. And now divide both sides by 75.15. And what do you get for this? 0.84. And what are the units of coefficient of friction? Nothing. No units, right. Okay, so if the coefficient of friction is less than 0.84, that box is going to speed up. Gravity is going to win over the friction, and the box is going to speed up down the incline. And if the coefficient of friction is higher than 0.84, friction is going to win over gravity, and the box is going to slow down until it stops. Any questions about that one? Okay, let's talk about circular motion. So the first question I have is, why are we doing circular motion? Why not square motion or elliptical motion or star motion? Or there's all these different cool ways a thing could move. Are we going to do all of them? No. So why bother with circular? Why single that out? What's so great about circular motion?
Because it's constant.
Yes, that is really kind of why. Because the wheels of the bus and many other things that share properties with wheels on a bus go round and round. So why circular motion? Why not, for example, square motion? And the answer is, when any kind of rigid objects change orientation, so when rigid objects change orientation, each point moves in a circular path around its joint. Okay, so here's an example. Like an angry Tin Man robot. If you track, as its jaw goes up and down, if you track the motion of this point, that point is going to follow a circular path around that joint. Isn't that awesome? You didn't know that. Don't act like you knew that beforehand. You didn't. Or if you have so you're lifting weights, you know? Muscle shirt. Every point on your arm, if this is the middle of your elbow joint, every point on your arm is moving in a circular path around your elbow. Come on. Okay, so it's not really that objects are more likely to move in circular paths than in other shaped paths. It's that when we start talking about rigid bodies, the relationships between points on rigid bodies require that points move in circles around the joints. So that's why this is sort of a lead-in to talking about rigid bodies. And circular motion, the idea is we'll know some extra stuff about acceleration and we'll use that information about acceleration to figure out forces in Newton's second law. So the most important ideas in circular motion, so that extra acceleration information in circular motion is based on the fact that the acceleration that's parallel to the velocity vector determines whether an object is speeding up or slowing down. And the acceleration that's perpendicular to the velocity determines the turning. And with circular motion, there needs to be a certain amount of turning the perfect amount of turning in order for this shape to stay exactly circular. So when I say turning, I'll say maintaining a circular path. We're going to give new names to these. The main ideas don't change. So all the stuff that we've been doing in lab with the parallel part of the acceleration and the perpendicular part, those ideas are still the same. But now we're going to call this parallel part the tangential acceleration. And that name makes sense. It's saying the acceleration that's tangent to the path. And when we've thought about the parallel part of the acceleration in lab, remember the way we do that is we draw a tangent line, and we know that that parallel part is always tangent to the circle. So that name makes sense with the way we've talked about it. And the perpendicular part of the acceleration we'll call the centripetal acceleration. Centripetal means toward the center. So that perpendicular part of the acceleration is always pointed towards the center of the circle. And there's one more thing that's going to be super useful that has to do with this centripetal acceleration, and that's that if this object is moving in a circular path, the magnitude of this acceleration is always equal to the speed squared divided by the radius. So v is the speed, r is the radius of the circle. And this always points, like the word centripetal suggests, it always points directly toward the center of the circle. Okay, so that's the extra bit of information that we always have when we're talking about circular motion. Not only can we draw the direction of that perpendicular part of the acceleration, but we know exactly what the magnitude is if the thing is moving in a circular path. That's the perpendicular part of acceleration that's required for the path to remain a circle. Okay. All right, we're going to break circular motion up into two categories. The first one is called uniform circular motion. This is when the speed is constant. An example of that is like tetherball problems. So if you have some mass on a cable rotating in a circle that's parallel with the ground, then the speed doesn't change as it spins around. Well, air resistance could make it change, but if we assume there's no air resistance, then that's a pretty good approximation. All right, so let's just think about what's going on here for a second. Okay, the speed is constant. I was just talking about all this stuff with acceleration. Why is there acceleration at all if the speed is constant? Yeah, right, because it's turning. So as long as as long as this thing isn't moving with a constant velocity, so a constant speed in a straight line, there has to be acceleration. And so even with the speed constant, in order to move in this circular path, there has to be the perpendicular part, the centripetal acceleration. So the total acceleration is equal to the centripetal acceleration plus, this tangential acceleration is 0 because it's not speeding up or slowing down. And that's just equal to the speed squared over r toward the center.
So why is it 0 on top?
This here, why is this 0? This tangential acceleration is the one that is responsible for something speeding up or slowing down. So in this case of uniform circular motion, we don't have that. And then the second category is just called non-uniform circular motion. Non-uniform circular motion is when the speed is changing. So an example is, this is a loop-de-loop. It's a guy in a motorcycle. So if you watch, like at the circus or whatever, when people are doing loop-de-loops like this, they're going really fast at the bottom, and then gravity's slowing them down. Even though their engines are cranking, they're at their slowest point right at the top. So the whole way around this circular path, the speed is changing. And in this case, A total is equal to A centripetal plus A tangential. We'll talk about how to calculate A tangential later, but what this says is that the total acceleration is equal to v squared over r toward the center plus A tangential. Okay, so that's the difference here is when the speed doesn't change, we totally know how to specify the acceleration in terms of the speed and the radius of the circle. When the speed is changing, we know the centripetal acceleration in terms of the speed and the radius, but we also then have to add this tangential part to it. So it's a little more complicated. Okay. In terms of the lab approach, the way we've been thinking about stuff like this in labs, uniform circular motion looks like this. There's the path of the object. There's the object. Say it's moving around a path this way. What direction is the velocity vector? The velocity is tangent to the object at that path in the direction of motion. So a tangent is like this. And then is it down or up? Down. So there's the velocity vector. Is it speeding up or slowing down? Well, this is uniform. So no speed change. So there's no parallel part of the velocity, no tangential part. It's turning, and so there's a vector in towards the center that's equal to the centripetal acceleration. And then non-uniform circular motion. Here's the path. Let's say this one is slowing down. What's the direction of the velocity vector? Down, same as before. If it's slowing down, what's the direction of the parallel part of the acceleration? Up. And now we're calling that parallel part of the acceleration the tangential acceleration. What's the direction of the perpendicular part? Toward the center. And we're calling that acentripetal. And then you add those two vectors to give you the total acceleration that in this case looks like this.
So it's like the same thing.
Yeah, it's just like we've been doing in lab. We have two new names for them just because people have picked these names already, so we don't get to pick them. But the concepts are exactly the same, and we have one new bit of information to add to this analysis, and that's that we can actually calculate that centripetal acceleration based on the speed and the radius of the circle. Okay? Any questions about that? All right, well, so next time we'll get into how to actually do problems.